So the big idea here, you saw this hopefully in your video, is that, wow, totally showed up. All right.
Yeah.
If you took the video of the stick that was rotating through the air, if you looked at just the center of mass, what did it do? It went in a parabola. And if you take a stick, like I take this popsicle stick and I put it on the table and I spin it, what does it rotate about? Does it rotate about its edge like this? What does it rotate about? Center. So if you randomly spin something, it'll rotate about its center of mass and not about any other point. Why is that?
Physics.
Objects are lazy.
Yes! That's why. Objects are lazy, which means what?
It's easier to rotate.
What's this fundamental principle of the universe? That,
Entropy.
Something like universal law.
universal law of, yes, increasing entropy,
That's crazy.
which could be stated another way as
Doing something the easiest way.
doing something the easiest way. And by easiest we mean what?
What takes the least energy?
What is the lowest energy state you can go to? It turns out that a stick rotating about its center of mass is less energy than a stick rotating about a fixed axis on one of its ends. Why is it less energy?
Because there's more mass in the middle.
Because it's based off of radius squared.
Ah, so what are you getting about more mass in the middle and radius squared? What's all that have to do with?
Inertia.
Moment of inertia, right? A stick's got less moment of inertia about its middle than it does about its edge, right? And from the last unit, we talked a lot about Newton's second law, which is basically what's going to be on the test. But this unit, we're going to get a lot more into rotational energy, which also depends on moment of inertia, right?
Yes.
Because what is the equation for rotational energy? Well, rotational kinetic energy.
Moment of inertia.
KE equals,
1/2 moment of inertia times the angular velocity squared.
nicely done. It's 1/2 mv squared, right? What's the rotational version of m and v?
Inertia and angular.
I and
Omega.
omega. So, if translational kinetic energy is 1/2 mv squared, rotational kinetic energy has to be 1/2 I omega squared, right? And what situation gives the smallest rotational, rotational kinetic energy? About the end or about the middle? Why? Is omega the same? What?
Yes.
Say it's spinning at a certain velocity, right? Omega is the same, but I is different. It's smaller, rotating about the middle. And it'll naturally rotate about the axis that will give it the smallest energy, because stuff is lazy. Got it? All right, just like you will naturally fall over and assume the lowest energy state possible. Unless you do something about it. Right? If I hold this stick right here, what's it going to do? It's going to fall over. Boom. Get to the lowest energy state it can get to. Oh, if given a chance, hey, it went even lower. Does that make sense? Okay. So, and I got some actual numbers here. Objects are lazy. Specifically, it takes the least amount of energy to rotate about the center of mass compared to any other possible axis. The most energy situation I have drawn here is about the edge. Well, the kinetic energy rotationally would be 1/2 mv squared. Wow. I'm not sure where I was going. Oh, I was just looking at the kinetic energy of the edge of the stick. So the kinetic energy of the edge of the stick is 1/2 mv squared, right? where V is L omega, right? Just a point on the end of the stick. Here, the kinetic energy of point 2 is 1/2 mv squared, but it's L omega over 2 for the V. Whatever. I forget about that. I like the I omega squared explanation better. Everybody's okay with I omega squared, right?
Mm-hmm.
Okay, moving on. Rotational kinetic energy, here it is. For a particle, an individual particle, I'm not talking a stick, but an individual particle rotating about an axis, what's its kinetic energy?
Half
1/2 I omega squared.
No! An individual particle!
half
It's 1/2 mv squared, right?
Yes.
Okay, good. So if I swing this thing, does it have kinetic energy?
Yeah.
How much?
1/2
Enough.
mv squared.
1/2 mv squared, right?
Yeah.
Doesn't matter that it's going in a circle, it's still got 1/2 mv squared, right?
Yeah.
All right. So, but it is going in a circle.
Yeah.
So,
It also has
could I relate the speed that it's going to how fast it's spinning, its angular speed?
Yeah.
What's the relationship between V and omega?
R omega. Or R omega.
V is R omega, right? So instead of writing V, I could write R omega, right?
Yeah.
Okay. So the equation would be 1/2 m times parentheses R omega squared, right?
Yeah.
That would be its speed in terms of omega. All right, fine, let's do that. So 1/2 m times R omega squared, which is right here. But if you do a little mathematical manipulation, that's the same thing as saying 1/2 mr squared omega. Wait, what's mr squared?
Inertia. Moment of inertia.
Ha! The moment of inertia of a particle. Guess what? It's the same thing. The moment of inertia, the kinetic energy of a particle going in a circle, if you use 1/2 mv squared, is the exact same as if you calculate it using 1/2 I omega squared. Woo! Everything is okay. The world works. So, kind of begs the question. If you wanted to know the total kinetic energy of a particle going in a circle, is the total kinetic energy 1/2 mv squared plus 1/2 I omega squared?
Wait, what?
Depends what you're giving.
Oh!
Wait, did you just add them together?
Is the total kinetic energy 1/2 mv squared plus 1/2 I omega squared?
No.
Which one is it?
Depends on what. Like they give.
It's either one or the other, but not both added together. Got it? So when you're doing a problem with a particle, you have a choice to make. You can do it in terms of 1/2 mv squared, or you can do it in terms of 1/2 I omega squared, but you are not allowed to say, oh, the total is 1/2 mv squared plus 1/2 I omega squared, because that's wrong. Got it?
Got it.
All right, cool. Now, if you have a rotating object, the kinetic energy, rotational kinetic energy is 1/2 I omega squared. How do you calculate a torque? No, sorry. How do you calculate work?
Integrate torque.
Work is what? Integral of
Force.
force
Times distance.
dr, force times distance, right?
Yep.
Okay. So rotationally it would be integral of, what's the version of force called? Torque
D theta.
d theta. So torque d theta would be rotational work. All right, and the idea behind that is if you twist something through a certain angle, say if you torque something through 90 degrees, you'll be doing half as much work as if you torque something through 180 degrees. Does that make sense? Torque and angle versus force and distance. All right, good. Law of conservation of energy. Does conservation of energy apply to rotating things?
Yes.
Of course it does. It's still the same equation. The total energy is still the kinetic plus the potential, and we're going to be using this all the time in this unit. So, now we have more terms. We have translational kinetic energy, we have rotational kinetic energy, which is new, we have gravitational potential energy, we have spring potential energy, and I think that's about it that we've covered so far this year, right?
Yeah.
Are there any other kinds of potential energy? Electrostatic, but we haven't done that yet, right? Okay, good. Okay, work energy theorem. What was the work energy theorem? Do you guys remember?
Work equals change in kinetic energy.
Work changes kinetic energy. So, what's the work energy theorem rotational version? Integral of torque d theta equals change in 1/2 I omega squared. Right. All right. Okay, so here we go. Capstan with a dangling mass. Wow, that sounds naughty.
Wow.
Nautical, come on. Come on, it sounds nautical. That's what I mean by when I say naughty. K-N-O-T. Not.
No.
What?
Okay, let's just really hit that ever happened and keep going.
It's like a triple pun. You've got to love it. Yes.
Aha.
All right.
I thought it was good.
Okay.
All right. Do you guys know what a capstan is, by the way?
No.
Okay, so let's say you work on a ship.
What holds the anchor?
And you have a ship, and you have, on the ship you have these things called capstans. They look like this. They're really just a spindle with stuff, with rope or a chain hooked onto it, right? And they go like that. Now, how does a capstan work? Well, most capstans, or I think actually the definition of a capstan is something that you can wind up and lift with, right? So you translate the rotational energy into translational energy by pulling up the rope by twisting the capstan. So this is a capstan right here. Wow, this is so convenient. It was sitting right here. All right, good. So what if you didn't actually apply any power to this? What if this thing was completely unpowered and I hung a weight off of it? What would happen? You go here. You hold one end of that. Okay. And then I'm gonna apply a weight to it. Ready? Oh, that didn't work. Our capstan broke. Sorry. Oh, we have a bigger stick to use. Let's use a bigger stick. There we go. Okay, so what happens if you pull down with a weight? Wow, he's heavy. All right. It unwinds, right? Nice job. Nice job. Okay, so that's what happens when you stick a weight on a capstan and you don't actually do anything to try to lift it. So, what kinds of energy are involved?
Friction. It's not an energy.
Forget about friction for now. We'll get to friction later. But assuming there's no friction, what kind of energy is involved?
Gravitational.
The gravitational potential energy of the mass. Okay. Initially, it's just gravitational potential energy of the mass. But after a while, what kind of energy is involved? Kinetic of what?
Of the capstan.
Here, let's actually hook a weight up to this so you can see it for real. God, we really need to teach a knot tying class in here because the fact that you guys don't know how to tie knots is a major issue. But you gotta know some basics like a bowline and a square knot. All right, so here we go. We're gonna actually try this. So we've got our capstan set up. We've got a weight. What kind of energy exists before?
Gravitational.
Okay, on the way down. Whoa! Oh, that went fast. What happened to that gravitational potential energy?
It turns into kinetic energy of the mass and rotational kinetic energy of the capstan.
Yes! We have two objects moving, right? We've got the mass that's falling, it's translating, right? And then we've got the capstan. It's not falling, but what's it doing?
Rotating.
Rotating. So we got two kinds of kinetic energy. Two objects moving. Each of them, one has a 1/2 mv squared, and the other one has a 1/2 I omega squared. So if you're going to do the law of conservation of energy for the whole thing, you've got to say that the mgh, starting out, gets turned into 1/2 I omega squared plus, of this guy, plus the 1/2 mv squared of this guy. Does that make sense?
Yeah.
You got two bodies to worry about. Well, that's interesting. So you could say that the MGA, well, we already said that, sorry. Very interesting question, though. What if you wanted to know how fast the mass is going after it dropped a certain height? How would you do it?
Take the change in potential.
Is the string massless?
Yeah, assume the string is massless, yeah. Yeah, we are not ready to start adding massive string to this. Oh my gosh. Right, sorry, go ahead.
Since you can relate the velocities of the ball, and then you know the mass and then the inertia.
Yeah. So you know that this thing is falling, right? You also know that this capstan is spinning. But you also know that the rate at which the mass is falling is equal to the velocity of the edge of the capstan. Which means you can relate the 1/2 mv squared and the 1/2 I omega squared, because omega is just the v divided by the radius. Got it? So if you do that, what you'll get is this. The 1/2 mv squared plus 1/2, let's see. Assume it's a disk, so it's a 1/2 mr squared capstan. Omega is v over r. What happens to the r's? They cancel. Well, that's interesting. Do you need to know the radius of the capstan to find the speed of the mass? No. Just as long as you know the moment of inertia is 1/2 mr squared, you're okay. So, if you do all the math on this, you get the 1/2 mv squared of the mass plus 1/4 mv squared of the edge, where v is the edge of the capstan. Big M's the mass of the capstan, little m is the mass of the mass.
Oh, string is
Right, the string is massless. We aren't doing changing mass capstan yet. That's a little penis. We might have to wait till college to get that version.
Wouldn't that just be an integral?
Yeah, it would be a problem that that's not simple algebra. And the whole idea with simple energy analyses is you don't have to do any calculus, which is nice. All right, so here we go. So, do a whole lot of mathematical manipulation and you get the velocity after it's fallen height h is equal to square root of 4 mgh over 2 little m plus big M. Isn't that pretty cool? Guess what you're going to have to do on homework?
This.
Yep. All right. Now, if the capstan didn't have any mass, how much energy would it have? None. So where would all the energy go? Into the 1/2 mv squared of the hanging mass. So if the capstan had no mass, what would it do to this equation? If this were 0, what would happen?
It would just be square root of 2gh.
It would be square root of 2gh. Where have you seen square root of 2gh before? Anytime you got something falling. That's how fast it's going after a certain distance. Square root of 2gh. You learned that way back in the beginning of your first year of physics when you did it. Make sense? Okay. Let's see if there's anything else. Ooh. Interesting. A falling rotating stick. What time are we out of here? Say you had a stick that was like this. falling. Is this a constrained version or non-constrained? I can't remember. Oh, no. This one is rotating about its edge. Like that. How fast is it going when it gets to the bottom? Wait, hold on. Let me say that again. What do you mean, how fast it's going when it gets to the bottom? What's that mean?
How fast is the center of mass?
How fast is the center of mass moving? That's one question.
How fast is a point on the edge?
How fast is the tip moving? That's a different question. Or what's the other question we could ask?
How fast is it moving rotation?
What's the angular velocity? Right? So those are three different questions. So which one do we want to ask? We're doing tip speed. Okay, so how fast is the tip of this stick moving by the time it gets to the bottom of the swing? Could you do this with forces
Yes.
and integration? Yes, you could. You'd have to integrate that angle from 0 to 90 degrees, or from 90 degrees to 0, or I don't know what angle you want to integrate. Some crazy angle. That's a big mess. If you're really bored, have at it. But I like solving it with an energy method, which goes like this. What kind of energy does the stick start with? MGH, right? What kind of energy does it end with?
Rotational.
Yeah, is it rotational or translational?
Depends on what,
Which method you're going?
Well, particle we said could either be rotational or translational, but is this hold true for a stick too?
No, it's only rotational
solid-
because the
yeah,
whole
this-
stick's not actually moving.
Yeah, the whole, because this piece of the stick isn't moving. Well, it's rotating,
But it's not.
but it's not
left,
translating.
right, or-
This piece of the stick is rotating and translating. A lot. It's translating a lot. This is difficult. Okay. Do you see the issue?
Yeah.
Is the stick rotating or translating or both? So here's what we got to do. The best way, I think, to deal with this is say that after it's rotated through a certain angle, it's got some gravitational potential energy based on its center of mass. It's got some rotational kinetic energy about its axis of rotation, which is this end of the stick. Does it have some translational kinetic energy? Yes or no?
No, because the axis isn't going.
That's what it says right now.
Wow.
Wasn't that from frame of reference?
Yeah, what's your rotation? Here's how you deal with this. Whatever you choose as your axis, that's the spot that you should use for your 1/2 mv squared and for your 1/2 I omega squared. So, if you choose your axis to be right here, is your axis got 1/2 mv squared? Does it have any v? No. Does it have any omega? Yes. Got it? All right. So, since the axis is not moving, you've got MGH and 1/2 I omega squared. Does that make sense to you? Whatever you choose as your axis, that's the point that you should choose for both your translational and your rotational energies. All right. And you can figure out, do a bunch of math, and you end up with the tip speed is root 3 GL sine theta. Wait, what if theta is 90 degrees? What about the bottom of the swing? Root 3GL. Wait, what was it for? Root 2GL, right? For an individual particle speed at the bottom? Wait, hold on, this is interesting. I should have had a demo set up for this, but I didn't have time. We're going to do a little experiment. Which is going faster at the bottom? This? Or this?
That. No, seems
So I'm asking a stick that's rotated about its edge that's the same length as a mass hanging from a bob. Are they both going the same speed at the bottom?
what kind of snow?
Ugh! Which is going fastest at the bottom, the stick or the bob?
The stick.
Why the stick? No. Just forget about the. Pretend like this capstan wasn't even here. You're just like this. Which is going faster at the bottom, or are they the same?
When you say fast, are you talking about an
The
angular
tip
velocity?
speed, the speed at the tip. Why is the stick going faster? The moment of inertia is less for the stick. No, I could have a really massive stick.
It's
You want a simple, stupid answer? The stick is square root of 3, and the bob is square root of 2. That's a lame answer, but what's the real reason? Science! I love it. What's the real answer? Think about moment of inertia. Think about where the mass is located.
The moment of inertia for the stick is to. Because the center of mass of the stick.
Yeah,
is
well,
relative to-
I mean, it doesn't necessarily have less moment of inertia.
no less potential to start.
Where is the mass located for the stick? In the middle. Where's the mass located for the bob? The edge. So, based on the location of the mass, it takes longer to swing the bob through 90 degrees, and it's going slower. Does that make sense?
The bob is going slower.
Yeah.
By the time it gets through the.
Take a look at the equation. All right. So I think we're going to actually do this demo the day after tomorrow.